Hello, my friends. This is going to be a series of videos on the latitude of the planets. We're going to start with Mercury, Venus, and Mars, and then we will talk about other planets. I'm not sure how many videos we will have in this series, but it will be at least a few. There's a lot of material to cover. And in making these videos, I have learned a lot. So there's new information. It was even new for me. And this, to me, is a very interesting topic because the latitude of the planets is so basic, so fundamental. It's like one of the most obvious things in the sky. And we're going to talk about the astronomy, and towards the end of this series, we'll see what ideas we have about interpreting it. Mostly this will be just about the astronomy, like what is latitude? A lot of fascinating details about heliocentric latitude versus geocentric and the unusual way in which some planets, for example, Mars, the way its latitude changes, it's fascinating. This is just a basic fact of astronomy that we overlook. And before we can interpret something, we have to have an idea of what it is. And latitude gets overlooked. So what really is latitude, and what are some of the fascinating things, some of which, again, I've just learned about myself in making this video. What are some of the fascinating things that happen with latitude? Okay, let's build this up from the beginning. And this won't take long before we have these basics down, and then we'll move on to other things. But even in covering these basics, there's some interesting things we're going to notice. Okay, so what is latitude? In the upper right corner of this slide, we see a diagram of the solar system. Obviously, it's not to scale. It's just to show some basic things about how planets move around the sun, how they revolve around the sun. Excuse me. So we have this yellow, pale yellow circle in the middle. That's the sun, of course. And then, as you know, the planets revolve around the sun, each at their own speeds. So there's Mercury as a gray ball, and then Venus. Where's Venus? This pink one. And then Earth, which is blue, and then Mars. We're just showing up to Mars in this image. And in this image, you'll see that Mercury is tilted relative to the other planets. The other planets look, well, more or less, maybe not exactly, but more or less in what we call the same plane. And by plane, you can see obviously what we mean by looking at Mercury. Mercury is tilted up on the right and tilted down on the left. That's what it's trying to show. Now, is that realistic? Is Mercury tilted? Is its orbit, as it goes around the sun, is it a little bit tilted in relationship to the other planets? True or false? So we've got the orbit of Mercury here in a different color to make it clear. It's this kind of bluish or turquoise color. Is that true? And this is going to be directly related to latitude. So you'll see in a minute. Is it true? Is that a reasonable image? Actually, it is. In this table, underneath the image of the orbits, this table here, this is a table of what we call some, not all, of the orbital elements. Orbital elements are basic characteristics of the orbit of the planet. There's a semi-major axis. That's basically a distance from the sun. So the Mercury is closest at 0.38. Venus is 0.72. Earth is 1 by definition. This is called an astronomical unit. And the average distance of the Earth from the sun is 1. So this is interesting. Mars is 1.5 times farther away from the sun than the Earth is. Jupiter is a little more than 5 times, and so on. Saturn 9.5 times. And interestingly, Uranus, Neptune, and Pluto are almost actually starting with Jupiter. You have an interesting thing of 5, 10, 20, 30, 40. within 1 astronomical unit, actually, yeah, within 1 astronomical unit, you have 5, 10, 20, 30, 40. Anyway, that's the distance from the sun. And the E is the eccentricity. Eccentricity means how round is the orbit. I'm going to show you that on the next slides. Let's come back to eccentricity in a minute. Right now, I put in bold inclination because that's the one we're focused on. And this is also the one that's related to latitude. Inclination. Inclination means how tilted is the orbit compared to the Earth. So the Earth, by definition, is 0. Here it says 0.0004005, but essentially it's 0. So Venus is tilted about 3.4, if you round this off to 1 decimal point, a little more than 3 degrees, about 3 1/3 degrees. It's tilted a little bit. But notice Mercury's tilted more, much more than any other planet except for Pluto. And you're probably aware of this. So Pluto has this huge tilt. Well, we could use a more specific term than tilt. It's called the inclination, and we use the letter I to abbreviate it. So this inclination of the orbit, how far it's tilted in relationship to the Earth and measured as the number of degrees. So if a planet orbits in exactly the same plane, it's like if you had a piece of paper, each planet is almost in the piece of paper. It's more like a thick book, and the planets are going around the sun somewhere within the thickness of the book. They're all tilted to each other slightly. So we measure it relative to the Earth. Mercury, bottom line, Mercury has a big tilt, 7 degrees, and that's what we're showing here. So this is something interesting. I mean, we don't usually think about that. Maybe it's not that important, but it is interesting that Mercury is tilted significantly more in relationship to the path of the Earth than any other planet, except for Pluto. And Pluto's got this crazy, huge inclination of 17 degrees. And this is where the north node is. Every planet has a north node, and opposite a south node, which is where the planet's orbit crosses the path of the Earth. And perihelion is where the planet is closest to the Earth. We're going to talk more about this in the next slides and get better visualizations of it. The thing I want to emphasize here is that if we look at this little image in the lower right corner with the black background, it's like an old-fashioned image of what an atom would look like, although now they know it's not exactly like that. But anyway, this image in the very, very lower right corner with the black background, these kind of rainbow-colored circles around it, with something orbiting around, with things orbiting around it. So our solar system is not like this, obviously. But it's interesting to think about it, that this is just the way our solar system is. We do not have things coming up over our heads and around us. Actually, there are so many objects out in we call the Kuiper Belt, and some of them do have enormous inclinations, but most of them are almost in the same path as the Earth. And among the large planets, they're all very close, but Mercury does have this larger inclination. Anyway, that's what's happening. The planets are not in a perfect plane. They're slightly tilted to each other. They're not extremely tilted to each other, usually, as we see in the lower right corner. It's nice to take a step back. Most of us already know this, but it's kind of cool to take a step back and just kind of meditate on it or think about it. It's kind of like an existential phenomenon. Well, that's interesting. I mean, that's just the way it is. Okay. Now, let's look at eccentricity a little bit. So eccentricity and inclination are two of the most basic ways that we describe how planets move. I mean, think about it. In astrology, we're interpreting how planets move and, where they are in the sky. It's nice to have an understanding of how the planets are moving, not just the way that we're used to looking at it, but just to know in general. And from a heliocentric point of view, from the point of view of looking down on the entire solar system, this is what it looks like. Now, this image took me a little bit of time to find. This is a realistic image. It is the actual path of the planets in the fall of 1996. So this was made by an astronomer. By the way, I have the website sources here if you want to check it out. So these are the actual paths. If you looked from the top right down, so we're looking down on the solar system, this is what it looks like. That's the actual path of the planets, and it doesn't change, hardly at all from year to year. So this happens to be for 1996, but this is pretty much permanent. I mean, it's not completely permanent, over thousands of years, you'll see noticeable changes, but it changes very, very slowly. Interesting. First thing I wanted to look at here is you see the sun, little golden yellow ball there, and look at the path of Mercury. This is the real actual path. Now notice that the sun is not at the center of Mercury. And you might also notice that this is slightly egg-shaped. It's it's longer, if you can see my cursor, almost vertical, slightly to the right of vertical. This orbit is longer in this direction and shorter in this almost horizontal direction. Can you see that? It's longer. That's because the path is an ellipse, and the path of Mercury is one of the ones that's more obviously an ellipse. And when it's obviously an ellipse, the sun is clearly not at the center. And let me go back to the previous slide. Eccentricity tells us how round the orbit is. So look at Venus. Venus has an eccentricity of 0.006. It means Venus's orbit around the sun is almost a perfect circle. Not exactly a perfect circle, but almost. And Earth has a fairly round orbit, 0.016. It's a little bit elliptical. Look at Mars. It's more eccentric, 0.09. And it's fun to look at and see. And Pluto has a very eccentric orbit. That means that Pluto's orbit is very egg-shaped. It's like a skinny egg. I'm going to show you some more images of this to make sure it's completely clear what we're talking about. What we notice here is that Mercury has a high inclination and a large eccentricity. This means that Mercury is tilted more, as we see here. It's tilted more. That's the 7-degree inclination. And going back to our next slide, it's more egg-shaped. More egg-shaped. So Venus, we know, is almost round. What's happening here is that the sun is almost exactly at the center of the orbit of Venus. So Venus, this white dot here, going around, this is almost, not exactly a perfect circle. How do I know that? Again, because the eccentricity of Venus is almost zero. How do I know the eccentricity is almost zero? Because astronomers tell me, and I believe them. And so there's the eccentricity, 0.006. Very small eccentricity means it's almost perfectly round. And notice that if you look at the path of Mercury within Venus, there's a bigger space here. This is because of the eccentricity of Mercury's orbit. So, and then there's the Earth. The space between Venus and Earth is almost the same, with a slight difference. That's because the Earth's orbit is almost round as well. It has a low eccentricity. And then Mars is lopsided. To make to make clearer what I'm saying, I've colored it in. Okay? What? Boink! I've colored it in to make it really clear what we're talking about. I've colored in, I guess it's a pale blue, kind of a, pale purplish blue color, like a lilac color, Mercury's orbit. And now I think it's even clearer that it's egg-shaped. And I colored within Venus's orbit this light green, and I think you can see very clearly in the upper right corner how much thicker it is. Much more space than here in the lower left. Why is that? Because it's Mercury's orbit that is highly eccentric, 0.2, if you remember, has an eccentricity 0.2, is more egg-shaped, and Venus is almost round. And it just so happens that Mercury's orbit is oriented this way. It just so happens that the long part is this way. Okay, we're going to go over this with more slides, so don't worry if it's not completely clear. I mean, all this is very simple. All I'm saying is that Mercury is very egg-shaped. Another way of saying that more technically is it has high eccentricity. Venus, large eccentricity, 0.2. Venus is almost round. Earth is not quite as perfectly round as Venus. It has a little more eccentricity. We saw that on the previous slide. And notice the path of the Earth. It's a little fatter, I think, over here towards the bottom. Looks like it's a little skinnier. In other words, the distance from Venus's orbit to the Earth's orbit. So there's a little bit of difference because Earth does have a little more eccentricity than Venus. But they're both fairly round. And then Mars, which has a greater eccentricity. What is it again? Let's go back. Mars eccentricity is 0.09. I mean, that's not nearly as big as Mercury, but 0.09 obviously is much bigger than Mercury and than Venus and Earth. So Mars has a fairly large eccentricity, and which means it's more egg-shaped. Now, this egg shape, better term for it is elliptical. Elliptical is more specifically what it is. This elliptical orbit, this egg shape, it just so happens that it's off-center this way. And I want to show you about this off-center business to make it clear. Let me go to the next slide. Here's what happens with the off-center. You can draw a perfect path of the planets. If you can just manually do it. All you need is 2 pins or nails or whatever it is you're sticking into the paper or wood or whatever you're doing this on. I once did this outside, and I put like 2 sticks in the ground and took a big rope. So you take a piece of string in this case and say 2 pins on a thick piece of paper, something, or a cardboard, and then you just stretch it. You take like a pen or pencil, stretch it and draw all the way around. That's an ellipse. That is a perfect ellipse, and that is the path of the planets. You can draw a perfect ellipse. It's that simple. And these 2 pins are called the focus points, or the foci. They are the focal points. They are the focal points. And the farther you spread the focal points, like here they're really far apart, the greater the eccentricity, obviously. If you pull these 2 pins closer to the center, right where this vertical and horizontal lines meet, if you pull them exactly together, like you just got rid of one of them and just put one in the center, then you have an ellipse with 0 eccentricity. That's a circle. So an ellipse with the 0 eccentricity is a circle. So you can spread these 2 focus points as far apart as you want. And again, the farther away they are from each other, the skinnier and longer your ellipse is, and that can be measured with this value called the eccentricity. Think of the word eccentricity. Eccentricity means literally off center. So it's a really perfect word. It's exact translation. How off center is the ellipse? Now here's another amazing kind of bizarre thing, or fascinating, maybe not bizarre, but fascinating, is that imagine that this ellipse is the path of the Earth. Now, the path of the Earth has a much lower eccentricity. The two focal points would be, near the center, but the principle is the same. Now, what's interesting is that the sun is at one of those focal points, and there's nothing at the other one. How did Mother Nature decide which focal point would be the sun? And then there's this like empty one, like a ghost sun, like a ghost focal point. There's nothing there. So one of these 2 points, let me say that again, one of these 2 points is the sun, and the other one has nothing there. Or this could also be the moon going around the Earth. Any object going around any other object in the sky travels in an ellipse. And you can draw an ellipse. You can just see. You don't even have to do it manually because you can visualize what's happening here. And so, again, fascinating thing is one of those points is the sun, if this is a planet going around the sun, or if this is the moon going around the Earth. One of these is the Earth and the other has nothing in it. Astrologically, we find this other point rather fascinating, don't we? Like, maybe there's some meaning to it. And actually, I talk about that in the videos on the Black Moon Lilith, which is essentially where this point is. So anyway, for the moon going around the Earth. So we have, this is the actual paths of the planets. I love this image because it's real. It's not exaggerated. It's not exaggerated for teaching purposes. We don't have to exaggerate it because it's already clear. You can already see that Mars has a more eccentric orbit. Now, I'm going to show you this. Here's where I just wrote in the values. Eccentricity of Mars, 1.9. Eccentricity of the Earth, 0.02. Venus, 0.01. Mercury, 0.21. That's rounded off to the second decimal point. We already saw that in the table earlier. But just as a nice visualization, all the planets, this image shows us the direct revolution. They're all moving around, around the sun. And from what we call top, astronomically, there is no up or down. It's arbitrary, which we call up or down. But what we call up, from that viewpoint, the planets are going counterclockwise. They all go in the same motion around the sun. As you know, from the Earth's point of view, geocentric, a planet may appear to go retrograde, but heliocentrically, they never go retrograde. They're all going around the sun at a fairly constant speed, not exactly constant. The more perfectly round the orbit is, in other words, the smaller the eccentricity, so for example, Venus, the more constant the speed of the planet. So Venus has a very constant heliocentric speed because its eccentricity is low. Mars will vary in speed more. And Pluto, which has a huge eccentricity, like it's a very skinny egg compared to anything else, it's going to speed up and slow down depending on where it is in its orbit. Okay. All right. So there we go. This is just to give you an idea of what these paths look like. And here's the other detail that I think is interesting, is where the perihelion is. So let's look at the orbit of Mercury, the innermost one that I've got in this pale purplish color. The perihelion of Mercury is 17 Gemini 44. That's the exact position in the autumn of 1996 when this astronomer made this diagram. How do I know that? Well, I can use the Sirius software, and I made a chart for September 15, 1996. That's, fall season. It doesn't really matter because this isn't going to change during the year anyway. It changes so slowly. And if I go to listings, planet or asteroids positions list, and I select the first one, planet positions list, that's one place in the program. There are other ways you can find this, but this is a handy way to find all kinds of different information, like where the nodes are, and if you just want to look something up. And here we see for Mercury, the true perihelion is 17 Gemini 14. Did I write that down? I might have a typo here. Where's my typo? I wrote 17 Gemini 44. Yay. It's 17 Gemini 14. Okay, doesn't really matter for what we're doing now, but it's amazing how many typos we humans make. Let me check Venus, 11 Leo 42. Where am I? Back to the Sirius software. Venus, 11 Leo 42. No typo there. Okay, so anyway, the diagram's essentially right. Mercury's perihelion, we want the true perihelion. The mean perihelion, is only 1 minute difference. It's almost identical. We don't have to get into mean versus, what mean versus true is anyway. And there's like 1 minute difference at most. So it's not like the moon's nodes where you get a huge difference. Although, look at this. The Venus true perihelion is 1142. The mean perihelion is 1128. That's more than a few minutes. So yeah, I hadn't really noticed that before. It's 14 minutes. So that get a pretty more significant possibilities. I didn't go through to see what all the differences are, but I use the true perihelion, and we're talking heliocentric right now. We're just talking about where things are heliocentrically. Later we'll talk about geocentric. So here's the point I want to make. This is all leading up to this point. Mercury's perihelion at 17 Gemini 44. I know it's over here because here's the egg shape. The elliptical path of Mercury. Perihelion means the closest point that Mercury gets to in relation to the Sun. There's aphelion. The way I remember it is ap. Starts with the letter A and is away. So I think ap away, like AA. And perihelion is closer. So the perihelion is at 17 Gemini. I got the typo, 17 Gemini 14. Let's just call it 17 degrees Gemini. Mercury perihelion is 17 degrees Gemini. Well, I can visually see that the closest point is over here somewhere. I mean, I don't know if I did it exactly right, but somewhere a little to the right of straight up is just visually, that's where 17 Gemini is, right? Because, it's obvious. The Sun is closest to this point over here. The opposite point of 17 Sag is where the Sun and Mercury are farthest away. And look, it's a big difference. Look how close the Sun is to the perihelion and how far the Sun is from the aphelion. Again, remember, this is drawn to actual scale. These are the actual size of the orbits and the actual shapes. Now, Venus's perihelion is over here at 1142. It's not going to be obvious because the Venus has almost a perfectly round orbit. The Earth's perihelion is at 12 degrees Cancer 51. And the Mars perihelion is at 6 Pisces 02. And Mars, which has a high eccentricity, as we notice, you can see that the distance of Mars, the path of Mars from the path of Earth and Venus is shortest over here, obviously. I mean, look at the pink on the lower right, very skinny, and look at the pink over here in the upper left, very thick. And we know Venus and Earth have almost round orbits, so this must be the perihelion over here of Mars, where Mars is closest to the Sun. And you could also take out a ruler or something and measure. But this is obviously the closest point of Mars to the Sun, and 6 Pisces to 17 Gemini. is a little more than a square. That's 101 degrees. And you can see, if we were to draw a square from the sun to Mercury and to the right, it would be just a little bit ahead of Mars. So this is pretty accurate. In other words, this X that I drew in green for Mars, I drew it in green just so you can read it against the pink and the dark blue. Anyway, this X here to show where the Mars perihelion is, roughly, I just eyeballed it. It's roughly over here. It's obviously somewhere over here where it's thinner. Where the pink part is thin. Maybe it's a little further up. It's somewhere around here. Is 100 degrees, 101 degrees, because 6 Pisces to 17 Gemini is a square with an 11-degree orb, and Mars is 11 degrees before the square point. And you can see it, a little more than 90 degrees. And from 17 Gemini to 11 Leo is 6 degrees less than a sextile. It's going to be about 54 degrees. So from here to here, I don't know, just roughly. You get the idea. That's a fairly good image of where the perihelions are, which leads to this conclusion that I have in the lower right corner. The egg shapes are pointing in different directions. That's just interesting. That the Mars egg elliptical path is oriented to where you know what I just realized? I think I made this more difficult than I have to. No, I had to do this. He's got Mars here at the aphelion. Mars is at the aphelion. The others are not shown. They seem to be random. But Mars is at the aphelion. It's opposite what I saw as the perihelion. So the elliptical path of Mars, you could say, is pointing towards this Mars image and towards the perihelion. That's the long part of the ellipse, and with the short part this way. So the perihelion shows you where the perihelion and aphelion show you the orientation of the egg, where the longest is, and specifically which one is the perihelion. So anyway, my point is simply this. The eggs are not all lined up close to each other. Mars is tilted a little bit differently. So you end up with a fairly complex looking image where the eggs are all different, and consequently the pink is thinner in the lower right, but the green is thinner in the lower left, because they're all like eggs pointing whichever way they're pointing. So this is the eccentricity. You now know what eccentricity is. You know how to draw it. Very simple. So if you were hand drawing the paths of the planets as they go around the sun, you might put, that you would put the 2 points for drawing Mercury in a line, and then for Venus, it's not going to be in the same orientation. They're not going to be both horizontal like this. They're all going to have their own orientation, and you end up with something that looks like this. Okay, so you know what inclination is, you know what eccentricity is, and I'm going to tell you one more thing. We're already at 33 minutes, so we're coming to the end of this first video, and I'm at a good stopping point. I'm going to show you just a few more things. We'll end this first video. Here's if we add the other planets. Here's an image where Jupiter and Saturn and Uranus and Neptune, and there's Pluto, and it's drawn in a purple color, tilted very much to the others. I think this tilt looks even slightly exaggerated. Well, whatever. Anyway, it's supposed to be 17 degrees tilt. Anyway, so that's pretty realistic also. And Pluto has high eccentricity. We noticed that. If we go back to the table, Pluto has let's go back real quick. Pluto's eccentricity is 0.25. Mercury's is almost as big, 0.20. 0.25, 17-degree inclination. So it's showing the highly eccentric orbit of Pluto, which means it's long and skiddy. And there's the sun far away from the center. You know, the center of this purple path of Pluto would be up around here somewhere, but it's way down here because you already know how to draw an ellipse, and you know that the focal point is not in the center, and it's very far from the center when the eccentricity is very large. And the sun is right exactly on that focal point. You know, I mentioned here in a previous slide that the planets travel in a geometric shape called an ellipse. Note sacred geometry. They don't call it sacred geometry in an astronomy class, and I don't recommend you use that term if you're taking a course in astronomy from astronomers. But it is fascinating that the planets make these perfect geometric forms. Just the way it is. Nature is built on these perfect geometric forms, and the planets travel in these ellipses. Actually, they get pulled a little bit away from the ellipse by the gravitational pull of other planets. And that's even understood as a movement of the ellipse shape. I talk about that in the video on the black moon Lilith, how astronomers understand the effect of gravity as a moving of the ellipse. Anyway, planets move in a perfect geometric shape called an ellipse. That ellipse is being modified by where other planets are. Okay. Now, this will be our last point, I think. Yeah, this will be our last point for this video. The inclination of a planet is also the maximum heliocentric latitude. We're going to just stop with this. We're not going to even do the bottom part of this. Let's just think about this as the final point of the first video in this series. Look at the sun. And if the sun is, you know, if you're on the sun, you're living on the sun, and then you look at Mercury and you look at the Earth, the greatest distance that Mercury can be above the Earth or below the Earth from the sun's point of view is the inclination. Well, you know what? Let's clarify that point and go over it in the next video. In the next video, we're going to go over, it's very simple and very obvious that once I show it to you, if it's not already obvious, that the maximum heliocentric latitude of a planet is its inclination. Let's go back to the table. So, for example, the maximum heliocentric latitude that Mercury can have is 7 north, when it's at its highest point, we call that north, to 7 degrees south at its lowest point. The most extreme heliocentric latitude that Mars can have is 1.85 degrees, a little bit less than 2 degrees, north or south. That's how far it's tilted. That tilt is how far it can go up above and below the Earth. It's just that simple. All I'm saying is that Mars is tilted almost 2 degrees, means it moves up to 2 degrees above the Earth to 2 degrees below the Earth. So you can also call that its maximum latitude. So inclination and maximum latitude of a planet, as viewed heliocentrically, is the same exact thing. It's the same thing. But what gets interesting, and we're going to talk about in the next video, is what happens to latitude geocentrically. And that is not simple at all. It's quite fascinating. And the maximum latitude of a planet geocentrically is not the same, at least the planets close to the Earth, especially Mercury, Venus, and Mars, is very different from the heliocentric. And we will see why, and that's what we'll talk about. And we're going to see some fascinating graphs of how the geocentric latitude changes. And a really important point we're going to be making also, just as a preview to the next video in the series, is that latitude is the most obvious thing other than the zodiac longitude in regards to the movement of a planet around the sun. It's the most obvious thing. If you're thinking about a planet's revolution around the sun, let's see, which diagram should I use? Let's use this first one. The most obvious thing about the movement of the planets around the sun is how far they've traveled around the sun. And geocentrically, we just point to the planet from where the Earth is. We just say, oh, Mars is over there. But the other obvious thing is the latitude. Let me say this again. When we think about how a planet is moving around the sun, just that's called, its proper motion. It's actual movement around the sun as it revolves around the sun. The other motion that's important is the planet's rising and then coming overhead and then setting. That's the diurnal motion. There are two basic motions. But the motion, just thinking about the motion of the planets as they revolve around the sun, and that's the zodiac longitude. That's the all-important zodiac longitude. We say like your Mars is at 5 Pisces or something, 5 degrees Pisces. That's that zodiac longitude. That's simply where the planet is as it goes around the sun from the Earth's point of view. What is the other thing you would notice about, say you're looking at Mars, and you're saying, okay, there's Mars. It would be conjunct the sun, for example, from the Earth. Here's Earth is this blue, and you'd say there's the sun, and maybe Mars is just past opposition, And the other thing you would notice about Mars is how far above or below the ecliptic plane it is. So latitude is the second most obvious thing. And some astrologers use the terminology incorrectly, and they will think that that's declination. They'll say declination is the other coordinate. It's the other dimension. No, it isn't. The other dimension is latitude. I have another video about what declination is, also an important thing, but it has nothing to do with this directly. So if you thought it was declination, it's not. It's latitude. So anyway, this second position, how far the planet is off the ecliptic plane, it's usually ignored in astrology, but it's the second most obvious thing about where a planet is as it goes around the sun, and also where we see it in the sky. If we were old-time astrologers who didn't have all these books and computers and we were going out, that's one of the things we would notice. We would notice where its zodiac longitude is, and we would be seeing, if we were professional astrologers back in the Middle Ages, we would be aware of how far above or below the ecliptic plane that planet is, because the astrologers in those days were astronomers and they were mathematicians, the great majority of them, and so they were aware of these things. Okay, that's it for now. This first video, we're already at 43 minutes, quite long, but it's to go over the basics of planetary motion. It's a little bit embarrassing that we astrologers interpret planetary motion and we're not that aware of it. And this is going to get more interesting. We're starting off with just the fundamentals. Maybe you already knew this, although just seeing the visualizations of actual orbits and how things are aligned, it's hard to find that information presented this clearly. But as we progress, we're going to see more and more interesting things, like I said, that I was not aware of. I don't think hardly any of us were, as we look at this in more detail. Okay, my friends, that's the end of the first video. I will continue with the second in a series of videos on latitude. So thank you very much for watching this first one in the series. God bless. Namaste.